Okay, thank you very much, Philippa. So I think you've already introduced my title. So the picture on the right shows you what I mean by some of the differences between a normal wide field on the top left-hand corner and what you might consider to be an optically sectioned image on the bottom right-hand corner, top left and bottom right. So I think we're all probably, a lot of us are probably familiar with these. The problem with optical microscopy, of course, is that we want to see things which are small, okay, and that requires us to use high numerical aperture objectives. So our lateral resolution is approximately lambda over NA. So therefore, if we want a small delta R, we want to have a big NA. But unfortunately, high numerical aperture imaging systems have a small depth of focus. So the depth of focus is approximately n lambda over NA squared. So as you increase your numerical aperture, you really reduce your depth of focus. So this is might be considered a bad thing because you see lots of blurry out of focus stuff. And that's all low resolution. It contains very little information, and it really just tends to get in the way. Or you might consider it a benefit because it enables you to if you can remove that out of focus stuff and leave that, you can leave the high resolution in focus stuff, and it enables you to increase contrast and let you measure structures in 3D. And this is what we're commonly using a lot of these high-end microscopes for these days. So the gold standard, if you like, which has been around for quite a long time now, is Confocal Microscope. Here's a standard slide I use in all sorts of teaching material. It shows you how it operates. We illuminate with a point source. When we look at an object in focus, the light coming back from where that point is focused on the object goes through a detector. When we look at something that's out of focus, it's blurred at the detector, a pinhole of the detector, and we see a lot less of the light. So we're actually blocking that out of focus light. And this is what gives us an enhanced resolution or an optical sectioning effect in the confocal microscope. So if we want to look at the resolution, we can actually work out what the point spread function looks like. We can work out for a conventional point spread function, and it's shown on the right. This is just a simulation for something like a numerical aperture of 1.2. We see we've got relatively narrow width at the center of that point function and slightly longer axial length. Now, this is quite instructional looking at this conventional PSF, because what we're seeing here is if we look just at the PSF, we see that even small objects, so a point is a small object, small objects section quite naturally by themselves. So the question is, why do we need a confocal PSF? So if we now take a confocal microscope, effectively we're looking at a square of this point spread function. So on the right, we have a confocal PSF. And it does look slightly smaller, but one of the things you'd find, because we're squaring that intensity, is the total amount of light in any one of the planes, is going to be, and any one of the planes out of focus, the total amount of light is going to be much reduced to what it is in conventional PSF. So in the conventional PSF, if we look at any whole plane out of focus, we'll find there's exactly the same amount of light. And that's because we've done nothing to reduce the signal there. Whereas in confocal, we've blocked that light because of our detection pinhole. Now, there's another thing I want to introduce, and that is one of the things we like to talk about as physicists and engineers and optics people is we like to think in Fourier space and particularly look at transfer functions. So here's a classic optical transfer function for an incoherent imaging system, which is what we essentially have when we look at a wide field microscope. What it is a plot of how well that imaging system images various different grid patterns, if you like. Okay, so at zero spatial frequency, we just have a plain image. And then as we go along the x-axis here, we're increasing the spatial frequency, which means we're decreasing the pitch of that grid function, and in fact we're now looking at finer and finer details. So it's telling us how well we can see different feature sizes in our object. So there's two interesting things here. One is, alarmingly, when I first started looking at things, I thought that was quite alarming. We don't see very much of the high spatial frequencies, but actually our eye is used to this. This is the way our eye works. This is what we see all the time. So we find that the images produced with this sort of transfer function look natural to us. Another thing which is useful to look at is how this changes with defocus. So if we increase the defocus, we go from the light blue to the red, to the green, to the dark blue lines, okay? And we can see that our higher spatial frequency components, particularly those that are around this level, they are rapidly disappearing. So as we defocus, we don't see these higher spatial frequency components. Alarmingly, however, we do see the zero spatial frequency component. And this is why in a conventional microscope, we don't have an optical sectioning technique. If we were to look at the same sort of graph for a confocal microscope, we now start attenuating these zero spatial frequencies. And there's an even more complicated way of looking at things. Well, this is just to show you the relationship between point spread functions and transfer functions. So in real space, we have images and point spread functions. We can Fourier transform those. We get our image spatial frequencies and our optical transfer functions. Okay, and these are related just by forward and backward Fourier transforms. So this is, to make it more complicated, we can look at our point spread function in 3 dimensions and calculate a 3D OTF. Now that's relatively difficult to display in all its glory, but one way of doing it is you can have an image like this, which is showing us our region of support. So there's outside this green donut shape, the optical transfer function has a value of 0. So we can't measure any of these spatial frequencies outside that transfer function. If we take a cross section through there, in the KX, KZ plane, you get a graph which looks a bit like this. So you can see here our limited region of support, but more often what you see is what's called this hidden cone. So in the center of the donut, we see this hidden cone, and those are spatial frequencies we can't measure. In particular, if we're trying to measure along this direction of Kx and Ky equals 0, we can only ever measure stuff right in the center. And this is another way of looking at the fact that we can't optically section. So if we want to generate an optically sectioned microscope, we need to start filling in that missing cone. So fortunately, if you do that with a confocal, we square our point spread function, so we get an autocorrelation of that point spread function in the Fourier plane. It does 2 things. One is it doubles the linear dimensions of that region of support, so we get higher resolution. Okay. Another thing is we've now filled in that missing cone. So this is one way of looking at why confocal microscopes can section. So if we look at that confocal versus conventional OTF, and I've done this in 2D, one thing you can see here is the increase in resolution. Okay, so the region of support has doubled along the linear dimension. This is our 2D conventional OTF, and this is our confocal one. However, confocal, it's vanishingly small, really, above a value of about 3. And this is one reason why confocals have never been that successful in increasing resolution. So, how can we measure this kind of optical sectioning technique? Well, the easiest way of doing it is to use a thin fluorescent sheet. So a thin fluorescent sheet is something which, when we look at it with a conventional microscope, will not, we can't tell when it's in focus, okay? Because it looks the same at any position in focus. And you can make one. So here's just a picture of one that we've made in the lab at Imperial. This is just a dye-loaded polymer which we spin coat about 100 or 200 nanometers thick onto cover slips and then seal onto glass slides. And this one contains rhodium 6G. So if you look at one of these, effectively as you refocus this, if you measure the signal level, you're probing the axial response. And that's related directly to what's happening along the KZ direction of our transfer function. So if we were to take the measurement of what's happening along KZ and Fourier transform it, we'd effectively get our axial response. So this is telling us how good our microscope is at rejecting out of focus blur. Okay, so in particular, it's telling us what's happening at 0 spatial frequency, it's telling us how it's rejecting out of focus blur. It's also telling us, by just making this one direct measurement, about what's happening along that axis of our optical transfer function in 3D. So, can we improve on that confocal microscope? So, there's a classic complaints about confocal microscopes. The spot scanning slower. Can we make it quicker? Lasers are expensive and limited wavelengths. Can we use cheaper conventional light sources like light bulbs or LEDs? Another aspect which has always been a useful thing with confocal microscopes is you had an analog signal you could directly feed into a computer and then do process that data. And this was even in the early times of confocal microscopes. But now, of course, computers are much more powerful. Are there techniques where we can leverage that power to generate optically sectioned images? And I'll quickly mention some of that. So here's an alternative way of doing things. If we were to illuminate our plane with some structured illumination, this is what one of those fluorescent sheets would look like if we illuminated it with various different patterns. Okay, so say we illuminated it with a spot, we just see a spot coming back, and this is the basis of a confocal microscope. Say we illuminated it with a grid pattern, we'd see a grid pattern come back, and this is the basis of the couple of microscopes I'm just about to talk about, including the Aurox ones. If we illuminated it normal wide field, we just see our plain sheet of fluorescence. Now, as we defocus, our spot will defocus, and this is how the confocal microscope's working, but also our grid, because it's a higher spatial frequency now, okay, we'll start seeing less and less of the spatial frequency. So if we can pick out that grid pattern from our image, it's telling us which bits of our image are in focus or not. And this is one of the classic ways of doing it. So this is something we came up with. It's embarrassingly, it's over 20 years ago now. It's the basis of what's used in ACoM and OptiGrid. We essentially we illuminate with a grid pattern, we move it to 3 different positions, and essentially we're looking for movement, we're looking for changes in the image. So you can add up all those images and get a conventional image. You look at the RMS variation across those images and you can get an optically sectioned image. And this is what's the basis of what we call optical sectioning SIM. Okay, so that's one technique. Another technique, which is the basis of what's used in Aurox systems, relies effectively on saying, can we parallelize that confocal microscope with a disc? And there are clearly lots of systems around which do this kind of thing now. Patran came up with this in 1968. Essentially put a bunch of pinholes on a disc and built a confocal microscope out of it and span it up. Okay, and you can get confocal images out of it. But the problem was you had to sparsely separate those pinholes in order to reduce crosstalk. So it's inefficient in the use of your illumination light. So our idea was to say, cool, can we? This again was about just over 20 years ago. Was can we do better than that? Can we do it more efficiently by essentially squashing those pinholes right up next to each other? And the end result, after a few more years of research, is what you see in the Aurox systems now. And essentially, they're a grid pattern on a disc, which we then rotate. Okay, so when we're in focus, we project this grid pattern onto our object. We see high contrast in the grid pattern coming back. We then project it back through the disc, okay, and onto a camera. So when it's in focus, the majority of the light goes through the disc. When it's out of focus, half of it hits the bright parts of the disk, half of it hits the blocking parts of the disk. Except we don't make those blocking, we make them highly reflective, and we detect the reflected light as well. So the transmitted light, we get essentially something which looks like a conventional plus a sectioned image, and the reflected light, we get something which looks like a conventional minus a sectioned image. We then take those into a computer. We have to do a bit of jiggery pokery. We have to align and register those and subtract them, and that results in us getting a sectioned image at the end. So how well does this perform? So here's some calculations on what our transfer function is going to look like for a system like this. So this is these are cross sections through that 3D OTF, and I've and the future simulations here, I've stuck with a 63 times 1.35 NA oil immersion lens, excitation at 462, and emission at 545, and on our system in Clarity, we're able to move the disk to different positions, and we're able to select different grid pitches here. So that's the distance between the lines, and the lines and the blocking areas always have the same width. So with this is for a grid pitch of 100 microns. So this means we've got 50 micron wide lines on a 100 micron pitch. And you can see here that we get a slight improvement in the region of support in terms of so a slight improvement in resolution. But very importantly, if we look in the XZ and YZ directions, we see that we're filling in that missing cone. And that's where we're getting our optical centric sectioning from. So we can do another calculation which says what does our sheet response to looking at a fluorescent sheet look like. And here I've plotted out curves of what this optical sectioning looks like for the three different settings that we use in Clarity, so that our disk has either 300 micron, 200 micron, or 100 micron pitch in it. Okay, and then I've also put in for interest a 50 micron pitch rating, and these are showing you that clearly how well it sections. It shows you why we've chosen a bunch of different grid pattern spacings. It's actually to be able to cope with a wide range of different microscope objectives, because different microscope objectives will have different a relationship between magnification and numerical aperture. But we're clearly sectioning, we get a strong focus for all of these strong pixel in focus for all of these, which then reduces as we go out of focus. As we go to a coarser grid, we do get more light through. And this is one of the reasons for doing it. If we got in order to match our, this is one reason you might want to change the grid pattern. It gives you a more signal. So your objects appear brighter, but it is at the expense of perhaps seeing more of the background blur. If we want to reduce that background blur to the minimum, we need to go for fine sectioning. So we're reducing a lot of, but that out of focus blur. It's not out of focus by very much. We get a smaller full width half maximum in Z. So our fine sectioning on this lens will give us a full width half maximum of about 720 nanometers. Okay, but we do see a less bright image. Interestingly, you can take this down further. So I put it in the curve for 50 microns. And here we go down to about 460 nanometers full width half maximum. But it's that area under the curve which gives you an idea of how bright your images appear. And in fact, this is, in users' hands, they prefer to see brighter images. And even if you were to look at an Apotome or OptiGrid system, they too will use quite coarse grid pitches in order to get more signal through the system. But it's interesting to compare this to the confocal. Changing that grid pitch or the slit width is very similar to changing the pinhole diameter in your confocal system. Okay, so here is a direct comparison in terms of our slit width and pinhole diameters. And you can see if one area diameter for this lens will be, a magnification will be 62 microns. And we can see some very, very similar performance between the two. You might even argue that perhaps that the grid response is better. One way you can look at that is to say, how quickly do these tails attenuate? And for a confocal, that only goes of the order of Z to the -2. So this is an interesting result of that sheet sectioning response, whereas it goes of the order of Z to the -3 for the spinning disk system. So these aren't necessarily the only way you can do optical sectioning. So just look at a couple of others. We could just take a wide field microscope image, and we know already that the problem is the low spatial frequencies. So if we want to get rid of that blur, can we remove it? So you could just go in and use an unsharp mask. So an unsharp mask effectively is a high spatial frequency filter. You'll find it in Photoshop. You'll also find it in ImageJ, in Fiji, which is where I've done this. And you can see that we can turn a wide field image into something which looks fairly much like a sectioned image. Okay, you can do slightly better than that. So this is an MSc project student I had work on this a few years ago. Taking the same image, you can do a slightly more sophisticated background estimation. And this is based on a technique that Galloway used in 2009 for spectroscopy data. You're estimating what the background blur is, and you can then subtract that off, and you get left with quite a reasonable looking sectioned image. But is it actually sectioned? What you have to ask yourself is, if I were to look at a thin fluorescent sheet, would I be able to filter out, would I be able to tell the difference between the response of that, the image of that thin fluorescent sheet and background blur? And effectively, you can't do it. With this sort of computational technique, you can't section a thin fluorescent sheet. Here's another example. So these are some SIM images from another project we're running in our lab at Imperial. Here we can see that this is super resolving SIM. So you're using a completely different processing technique, and the aim in here is to improve resolution. And you can see for our wide field image, we're getting some clearly improved resolution. All these blobs on the left are turning into small spots on the right. However, what the big problem is the bigger blobs are starting to disappear. So we don't see larger features in that super resolved image. And part of the reason, if you've ever looked at doing any sort of 2D, this is a 2D super resolution system, you'll see that it uses internally filters for as part of its Wiener filtering approach. And if we deliberately attenuate those low spatial frequencies when you do so. So here again, you can see I put in different color channels here, the high spatial, the high resolution image, and we can see the blue background blobs aren't coming through the system. So a TB super resolution SIM image also has problems in optical sectioning. It achieves it by filtering out low spatial frequencies. The same is not true of 3D SIM methods. So there are lots of 3D SIM methods out there at the moment where you're changing the structure of the illumination in the Z direction as well, and then you can do some optical sectioning. So there's just a few ideas here talking about optical sectioning. So I put in a final slide here, just as a conclusion. So we have a bunch of true optical sectioning systems. So our confocal system, SIM systems, structural illumination systems, so optically sectioning, and sometimes super resolution SIM systems are capable of doing it. Spinning disk systems like Nipkoff or the Clarity systems do it, as well multi-photon light sheet, and even some hybrid systems which might include parts of each. So a SIM and a light sheet, for instance, can do that. And that's actually the basis of one of our projects, is looking at SIM in light sheet form. Where you're likely to have problems doing true optical sectioning is some super resolution SIM methods, the 2D ones, and then computational methods. So does fluid convolution let you section a light sheet? It's something we need to look at. ask yourself very carefully. And another one is machine learning. So machine learning is becoming very popular now. You can apply it with lots of different types of optical techniques, and some of them will let you get an optical sectioned image, truly optical section, but some others will have some trouble. And that's basically because that optical sectioning information isn't there. So really, so the conclusion here is, if you want to think about how well a microscope sections, think about how it's going to operate when you look at a thin fluorescent sheet. Okay, so just some final acknowledgements. Some of the projects which we've been involved in, looking at structural illumination microscopy over the years, and below as well, some of the people who've helped out. Okay, thank you very much.
Thank you so much, Mark. That was fascinating. I think everybody would have learned a lot today. Now, Kirti Prakash from NPL has put his hand up to actually ask you a question live, if that's okay. We do have a couple of minutes. We have a little bit of spare time. So, Kirti, do you want to turn on your video and microphone and ask your question to Mark?
Yeah. Hi, Mark. So one of the questions is, what's the finest grid pitch you can have? So you mentioned 50 microns. So the dyes these days, they are getting brighter and brighter every day. So I started to wonder if you can go like 10 microns, 5 microns, and then get even better resolution, especially if you combine with DNA paint or something also.
So it's going to be very similar to a confocal response. So confocal, as you take down the pinhole size, essentially you will, if you start going below 1 area diameter, you do start getting an improvement in lateral resolution as well as axial resolution. But effectively that then levels off. So if I were to reduce the pinhole or the slit width size in each of these even further, I'm unlikely to improve the resolution greatly, or all I'm likely to do is reduce the signal level. So effectively, that resolution enhancement plateaus off. And one of the big issues that you start seeing is that if you reduce your signal level, particularly in something the spinning. One thing I didn't talk about here is the spinning disc systems is a subtraction system. Okay, so we're looking at the differences between two images. So we're subtracting out the optical blur. We can still see the noise associated with that optical blur. So you don't want this peak to become too small. Okay. So we will not see a much enhanced resolution beyond what you can see here at that sort of pinhole diameter or slit width.
Sorry, just one more question, Kirti, if that's okay, just in the interest of time.
Okay, so Mark, like you mentioned, so what keeps you away from doing super resolution sim? It seems you have all the elements to do that, right? You have the grid and everything, so it's just like looks like a computational thing now.
Well, okay, if we were to look at the way this works, we illuminate with a grid, we pass that back through our disk, okay, and we can see the difference between in focus and out of focus light, but we can also still see the grid. Okay, and that's when we look at a system like this. That's why we have to take 3 images. Okay, so we take 3 images and process those as you would do in a super resolution sim system. Okay, but here the way we get rid of the residual grid pattern is we then spin the disk. So that part of the processing is taken care of for us by spinning the disk. Okay. Now we can no longer see the grid pattern. We don't have that opportunity to do that sort of processing that gives you the super resolved image. However, there is some work we've done looking at, and some other people have done, looking at can we get some super resolved image data out of a disk system like this? And in fact, by using different types of disk patterns, not just a simple grid. Effectively, you're doing a sort of homodyne detection. You have to use a laser illumination when you're doing this, and you can start to see some enhanced resolution when you do so. Okay, so you can get systems which, in theory, at least, should give you up to the same sort of resolution super resolution SIM system. Okay, but it's a difficult sort of system to align and keep running in a decent fashion.
Okay. Brilliant. I hope that answered your question, Curti. Feel free to carry on in the chat window. I think Stan Botchway just wanted to ask you a quick question as well, Mark, and then we'll move on to Patrice's talk afterwards. So if Stan, if you're there, feel free to unmute and turn on your video. He's just got to raise his hand again.
No, I need to bring Stan in first. Yeah. We can only support 6 speakers at a time. So if Stan raises his hand, I can bring him in.
Well, if he doesn't raise his hand, he mentioned in the chat folder, can you comment on the fact that the ARIScan system uses an area unit less than 1?
No, so that's an interesting question, is how well does an ARIScan system section? Because effectively an ARIScan, as far as I understand it, typically they use an array detector instead of a pinhole detector. So they are detecting this out of focus light. What an ARIScan is doing is it's giving you an effective pinhole diameter, which is small, although it's collecting more light by collecting it over a larger area. Okay, so that's how they give you an enhanced lateral resolution, right? I've not done the sums to see how that impacts your axial response to a sheet image, but I suspect because they're detecting over a larger area, you're likely to have a sheet response which might look very similar to a confocal pinhole diameter, which is the same as the diameter over which they're detecting light.
Okay. It seems that your talk has raised a lot of questions. So would you mind staying on for a little while, Mark, and watching the chat folder, and maybe you can carry on your conversations there.